One of the keys to successfully using simple moving averages and a lot of time series error measures is just staying organized. The calculations themselves aren't all that complicated. You can really see that in this scenario. Let's look. Livingston Medical Services is considering how to forecast demand for future non-emergency medical transportation. Okay, here is the past data. So we have 9 months of past data on the actual number of transports. One assumes these transports refer to the non-emergency medical transportation. Okay, fine. Livingston is considering a simple 3-month moving average or a weighted 3-month moving average where the past month would receive a weight of 0.8 and the other 2 months a weight of 0.1. Oh, okay. Now way at the bottom of the page it says, how would these two techniques have performed if they were in use during the past months? Let's back out for a second. Very often to select a forecasting technique to use in the future, one method of selection is to pretend like we had been using that technique in the past in order to calculate the error measures on the forecasts that would have been generated in the past. We assume then that the forecasting technique with the best error measures on the simulated past would be the best one to use in the future. That's kind of the context for what's going on here. Now, before we go any further, we should just check that we understand the two techniques we're being asked to assess in this fashion. The first one is the simple 3-month moving average. Now, for example, if you were using that and you were curious what would be the forecast for July, I'm just making this up, okay? Ignore the question at the bottom of the page. It would be really, really easy to calculate July because you would just average the past 3 months, which are June, May, and April. That would get you the forecast for July. Now notice I'm not writing down the forecast for July. You could average those numbers together and the number on your calculator is the forecast for July. I'm not writing it down here because I don't want to confuse the issue. That forecast, as nice as it would be, doesn't really help us answer the question that is asked at the bottom of the page. Okay, so I'm just discussing how you calculate simple moving average. Likewise, and you say, oh yeah, I know how to do that. Likewise, a little review. Do you remember weighted moving average? What if the question was July, right? You know, well, given this information, what would the forecast be for July using a 3-month weighted moving average? If that was true, see there's room for some scratch work here. What you would do is you would take, now see the past month would receive a weight of 0.8. You would take the past month, which if July was the question, this would be the past month, June. You say, okay, it's that number, right, and you'd multiply it times 0.8, multiply it times the weight, plus there are 2 earlier months, right? They each get a weight of 0.1, but you'd have to retrieve what they were. In the case of July, they would be the actual for May and the actual for April. So I would just fill in those numbers. That would get me the forecast for July. Oh, all right. Now, I'm not going to write it down because we don't actually need the forecast for July. It asked us how would those two techniques I was just talking about have performed during this past interval of time, which doesn't include July. Oh, all right, so now we need to actually simulate the use of these two techniques in the past. We're going to need a lot more room for scratch work. That's why if you have the note frame, let's start first with the simple moving average. There's just a lot of room in here to work. Right, because first off, I had better draw some lines so that I stay organized. There are 9 months of past data. So I'm going to make myself a grid with 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, because that's the span of time that I'm working with. The months we can see right here, and actually the actuals we can see right here. So just for convenience, I'm going to copy them over. Okay, our months are October, November, December, January, February, March, April, May, and June. Nice and bold, so I don't lose track of their identities. The actuals, let me get that where I can see it. The actual for October was 10,230 transports. So I'm just copying data. That's all I'm doing. The actual for November, more transports, 12,004. The actual for December, it went back down, 10,990. The actual for January, 12,480. The actual for February, 11568. The actual for March, 13244. For April, 15560. For May, 16034. And for June, finally, ooh, big month for non-emergency medical transports, 23,400. Oh, all right. Now, I said what we needed to do here was simulate the use of, what we're starting on is the first technique, a simple 3-month moving average. It's time to do that. Notice that in our simulation, we can't start simulating until the 4th month because we need 3 months of past data. That means our first forecast in this simulation that we can cast is for January because we have December, November, and October to average together. And I did that, and I got that that was an average of 11,075 non-emergency medical transports. That's our forecast for January. For February, we want to average together to create a forecast. Now notice that you're looking at the actual for February, right? We actually know what happened in February. We're pretending like we don't know what happened in February because this is a simulation. So what we want to do is ignore that actual for February, grab the past 3 months. That would be this 12,480, this 10,990, and this 12,004. I get that that's an average of 11,825. Then likewise for March, you want to average together December, January, and February, the 3 previous months. I get 11,679. For April, I get an average of 12,431 when you grab the past 3 months. For May, 1, 3, 4, 5, and 7. And for June, 1, 4, 9, 4, 6. These are the forecasts. Okay, now what we've been commissioned to do in this scenario is to assess how well the 2 techniques did. How well did this technique do in this simulation of the past? Oh, we have to calculate error measures. Have to calculate error measures because that's our measure of how well. Okay, well, that means we first have to calculate error. Error is actual minus forecast. So that's the next column in our table. Error is actual minus forecast. Here is the actual, right? Here is the forecast. So the error in January is 12,480 minus 11,075. On my calculator, I get an error of 1405. So I'm just filling it in. In February, 11,568 minus 11,825 tips over into the negative, a negative 257. I get an error in March of 1,565, an error in April of 3,129, in May, say 16,034 minus 13,457, I get an error of 2,577. And then in June, oh boy, 23,400 minus 14,946 is a whopping error of 8,454. Now, first off, what would we ever do with that information? Now that we have this information right here, we could use it to calculate the so-called mean error. The mean error of the forecast is just where you average these together, and I get 2,812. Is that good or bad? Well, right now we don't really have any context in which to interpret it, although one of the things that we'll note, just to remind ourselves, is that mean error is a really lousy measure of accuracy because it lets errors wipe each other out, you know, positive and negative, but it's a good measure of bias. But anyway, we'll come back to that when it's time for interpretation. We need to calculate some better measures of accuracy. All right, another measure of accuracy and a better measure is mean squared error. In order to calculate mean squared error, you have to first calculate the squared errors. See how that's a column here? Which is to say, just take each error now and square it. All right. If you say 1,405 times 1,405, that is to say you square it, I get, ooh, big number, 1974962. Okay, if you say negative 257 squared, I get 65878. If you say 1,565 squared, I get 244882. In April, if you square this error right here, I get 9792727. In May, if you square 2,577, I get 6639211. And stand by. In June, if you say 8,454 squared, 71470,116. All right, what are we supposed to do with these numbers? Average them together. Average them together because when they're averaged together, that is the so-called mean squared error, which I get 153,98513. That's a really big number. Yes. Is it good or bad? Don't have anything to compare it to yet. But as long as we are now assessing the simple moving average, might as well calculate some other measures of accuracy. Oh, right, because the one thing that's not so nice about mean squared error is that when you square an error, it explodes into a larger number. So it tends to exaggerate the larger errors. Another method for measuring accuracy is to simply average together the absolute values of the errors. That's why we have this column here for absolute error. That is to say, go back to the original error, and if there was a negative sign, like right here, just drop it. Well, most of the time there wasn't, which means I'm just copying these numbers straight over again. That's okay. At least it gives me a column here. This one, to average together. When I average those numbers, that's called the MAD, for mean absolute deviation. Another term for absolute error is absolute deviation. Average those numbers together and I got 2898. Interesting. A number that's not too terribly different from the mean error. You know, we might want to come back to that fact in a little while. But anyway, whether it's good or bad is kind of hard to, just looking at that number directly, get any sense of it, which is why there's one last column to fill out here in our assessment. And that is, you said it says percent absolute error. Yes, percent absolute error One of the things that we need to remember is that percent error has a definition. It is error divided by actual. So percent absolute error is just absolute error divided by actual. Well, we have both here on this sheet. It wants absolute error, so I say the absolute error divided by the actual. The actual is all the way back here. Oh yeah, okay, so I'm working with these columns here. So if I say 1,405 divided by 12,480, I get 0.113 some odd on my calculator, or essentially I'm going to write it here as a percent. About 11%. That is about, in terms of absolute error, an error of about 11%. Oh, okay, now I need to do that for each one of the months. So I say 2,000, or excuse me, not 2,000, no, 257 divided by, where's the actual? It's over here, 11,568. Not much of an error in the great scheme of things. I get about 2.2%. Here, this number divided by that number, stated as a percent, 11.8%. This number for April divided by that number for April, you'll see 0.201 some odd on your calculator, or an error of 20.1%. In May, that number divided by that number is an error of 16.1%. And then finally in June, this number divided by that number is a pretty big error. It's on the order of 36.1%. All right, why did we calculate those? Because now we want to average them together to create the so-called MAPE, mean absolute percent error. It's the average of these, which I get as an average of about 16.3%. Oh, all right. Now what we have is actually a series of scores on how well did the simple 3-month moving average work over this instance of past data. We were asked actually to compare it to the simple weighted moving average, which means that in order to comment on the original question, and so it's all about staying organized, we need to do essentially this table all over again, except for the other forecasting technique. Which is why, if you have the note frame, there's yet another page with plenty of room for scratch work. Simple 3-month weighted moving average. We gotta start all over again. Well, sort of. Certainly I do. Because first off, 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got to set up all 9 months again. I've got to set up all 9 months. Let's see, they started in October, November. This was December, January, February, March, April, May, June. Okay, those were the months. It's the same actuals as last time. Let me find the, remember this, actual table, and copy them again. Okay, the actuals for October, 10,230. It's that same data we were working with. For November, 12,004. This is all past history. We already know what happened. December, 10990. January, 12480. February, 11568. March, 13244. April 15560, May 16034, and June, big month for non-emergency transport, 23,400. Okay, now they're asking for in the forecast column, right, the weighted moving average. All right, that means that I, again, can only start forecasting in January. That's really where our simulation starts. But in order to create a number to copy in here for January, what I need to do is look at, well, what's the most recent past month? That was December. That was, a little bit of scratch work here, 10,990. That is what I multiply times 0.8. Or another way to think about it is I take 80% of that, and then I take 10%, or the weight is 0.1 of November, and I take 10% of the next most recent month. That's the scratch work for January right here, because I get a forecast of 11015. Put that in the calculator. I'm going to keep this rounded to integers because we're talking about the number of transports, right? So I get a forecast for January, somewhat different slightly than what we got earlier with the simple weighted moving average. I get a forecast of 11,015. Now I need to do this for each one of the months. I'm pretending like we had been using weighted moving averages. If I had used that same template to forecast February by giving January the heavy weight of 0.8, so on and so forth, I would have gotten a forecast of 11,825. Now, if you'd like to calculate these, you could check your work against mine. Here's what I got as a forecast for March, 11,679. For April, a forecast of 12,431. For May, a forecast of 13,457. And for June, a forecast of 14946. All right, those are the forecasts. The next natural step to assess those forecasts, right, is find what was the error in each one of those forecasts. Well, that's just actual minus forecast. I get an error here for the weighted moving average of 1465 for January. This minus this, another negative error for February, but it's a negative 715. The error for March, 1643. The error for April, 2560. The error for May, 1105. And then the error for June, the 23,400 minus 14,946, 7692. These are the actual errors in each one of the forecasts, indicating a mean error. If you want to calculate that by averaging them together, I get a mean error of 2292. All right, and we noted before that mean error may be useful later in our commentary, but it's not really a very good measure of accuracy, right? Other measures of accuracy, for instance, mean squared error, calculate that. We first have to square each one of these errors. Take that number right there in January, 1465, square it. I get 2145053. Take this number in February and square it. I get 511797. Take this number in March and square it. I get 2698135. In April, if you say 2,560 times 2,560, I get on my calculator 6553600. In May, a squared error of 1220583, and in June, take this number and square it. I get 59173018. What are we supposed to do with these numbers? What do they mean? They allow us to assess the mean squared error. I just average these together now, and I get a big number, 12,050,364. Oh, but we say the mean squared error actually tends to exaggerate large errors. All right, so maybe we want to calculate the mean absolute deviation instead. What we would have to do first is copy the errors except drop any of the negative signs. Well, that's easy because there's only one of them here. In February, instead of negative 715, I just have 715. Otherwise, I am just copying the error column because there weren't any other negative signs. Okay, this one right here, average those numbers together to find the mean absolute deviation. That's what it's called, the average of these numbers. I did that. I get 2530. And then we say, well, that doesn't give you a sense of scale. Percent error gives you a sense of scale. Mean absolute percent error can be averaged together to create the so-called MAPE. Okay, we better do that now. What we want to do is take each of the absolute errors and divide by the actual. Okay, so it's that column, this number, divided by this number in January. I get 11.7%. This number, 715, divided by that number in February, I get an absolute percent error of 6.2%. This number divided by that number in March, an absolute error of 12.4%. Then for April, an absolute error of 16.5%. Then in May, that number divided by that number, an absolute error of 6.9%. And then finally in June, this number, 7,692 divided by 23,400, is a 32.9% error. Take these numbers, average them together, that produces the so-called MAPE, the mean absolute percent error, of which I guess like 14.4%. You say, oh, okay, well, great. Now wait a minute, why were we doing all of this? Because, are we done? We're not quite done. Okay, we're actually to the exciting part because we get to answer the question, but we better go look what the question actually was originally. It says, how would these two techniques have performed had they been in use during these past months? We have that information now. And it is interesting to contrast the two techniques. This was the simple. This was the weighted. I'm seeing some similar numbers when I scan from one to the other. You know what? I would say in commentary, other than just reporting these numbers, I'm looking at these percent errors. Commentary, how would the two techniques have performed? Not great. Not great. You could cite, for instance, the fact that even the best one has a mean absolute percent error of about 14%. I mean, oh, wait a minute. What is it that we want to see? I kept drawing these boxes and saying that's the score, that's the score. We want to see 0 or close to 0, right? That represents what's ideal. We're not seeing super impressive numbers here so far. We don't have anything else to compare them to, but I'm not impressed. They're not very close to 0. You could comment that the weighted moving average appears to be doing a little better. This is simple moving average. See, that's 16.3, whereas this is 14.4. That's closer to 0. Also, look at, for instance, the MAD 2,530 for the weighted. The MAD here, 2,898, it is also larger. We could say, fair enough, weighted average appears to be performing slightly better. You know, C, MAD, or MAPE. that at that point has, especially then if you also report the error measures, basically answered the question. Although, you know, in reality, if somebody had asked us this question, there is something that we have discovered, if we know how to recognize it, that is kind of disturbing about, again, both of these techniques. And it goes all the way back to a comment that I made about the ME, the mean error. Do you notice that in both cases, this is, for instance, the simple. Here's the mean error, here's the MAD. These two things are not the same number, but they're pretty similar to each other. And here, this is the mean error, that's the MAD. Oh, this is nicer with the weighted moving average, but we're still talking about 2,000 some odd. They're still very, very similar. Why is this disturbing? Another nice note that you could make in reporting on this is both techniques appear to be strongly biased in their forecast. Both appear biased. You say, huh? What? What is bias? Go back and for either one of them, look at the errors. Okay, this is the weighted one, which we're saying is slightly better, but still. Do you notice that there's only 1 month where there's a negative error? What that means is over this simulation of 6 months, in 5 out of the 6 months, the forecast was too low. In 5 out of the 6 months, the forecast was too low, which resulted in a positive error, which meant that when you were averaging together the errors, they didn't cancel each other out. Oh, so that you got a big fat mean error. That is indicating that there's a bias. There's a tendency to forecast too small. This is something that's disturbing in a forecast, and is also something that you would want to note if you were doing this type of assessment. Because if the forecasting technique is tending to make the same mistake over and over again, that is not a mistake that essentially we would want to repeat in the future. So we might add that to our report. Basically, we've calculated each one of the error measures for the 2 different techniques, pretending like we had been using them over those 6 months. We are not really impressed with either of them.